Reaching for fine-tuning prematurely is like reaching for a database migration when a config change would do. Man, think about that for a second. If you wanted to hang a picture frame, you wouldn't rent a crane, right? No, you just grab a hammer. Yet, in the world of AI building right now, we see people reaching for the heavy machinery of fine-tuning all the time, when honestly, a simple prompt would do the job perfectly. Welcome to this explainer. I am so excited to be sharing this with you because today we're laying out the ultimate tactical playbook for 2026 AI engineers. We're talking about tactical fine-tuning for open weight models. We're going to completely strip away the hype, look directly at the reality of building with AI, and figure out exactly when and how to actually wield this incredible tool. Okay, let's dive into this. Here's the funnel we're about to explore. First up, to fine-tune or not. Second, the three major approaches. Third, why it's absolutely all about the data. Fourth, we'll walk through a 7-stage workflow. And finally, we'll look at exactly how fine-tuning fails. All right, section 1, to fine-tune or not, the 3-tool decision. Because before we even pick up the heavy machinery, we need to make sure we're actually on the right construction site to begin with. So here's the core mental model you really need to internalize. Prompt engineering modifies what you say to the model. RAG, or Retrieval Augmented Generation, modifies what context you give the model at runtime, but fine-tuning modifies the model itself. It's literally altering the underlying weights. So yeah, it's way more permanent and reliable than just putting instructions in a prompt, but as you'll see, it requires significantly more operational effort. As a builder, you're essentially facing a 3-tool decision. When you evaluate the costs, prompt engineering is your lowest cost. I mean, it takes minutes to iterate, and it's fantastic for instructions. RAG sits right there in the middle, at a medium cost, perfect when your model needs up-to-date or proprietary knowledge. And then there's fine-tuning. This is the absolute highest cost. We're talking training compute, rigorous evaluation, ongoing maintenance, the whole shebang. You really should only pay this steep cost when you desperately need consistent behavioral patterns that the cheaper options just can't enforce. So, when does fine-tuning actually earn its keep? Well, there are 5 very specific scenarios. First, when you need a consistent style or format, like a customer support agent that strictly adheres to your brand's voice. Second, domain-specific reasoning. Think of a legal research assistant that has to parse local case law. Third, strict output schemas. We're talking complex, nested JSONs where prompt engineering just can't give you a 100% guarantee. Fourth, high-volume specialized tasks. Listen, running millions of classifications on a smaller, fine-tuned model is vastly cheaper than calling a giant general model every single time. And fifth, when your proprietary labeled data is your actual competitive advantage and you want to bake that moat right into the artifact itself. Moving on to section 2, the 3 major approaches. We've got full fine-tuning, LoRa, and QLoRa. So say you've looked at your workload, you've tried prompt engineering, and you've decided you absolutely definitely need to fine-tune. Which approach do you actually take? Think about this number, 1%. Just a few years ago, fine-tuning meant modifying every single parameter in a model. If it was a 7 billion parameter model, you updated 7 billion weights. We call that full fine-tuning, and honestly, it requires massive compute. But today we have something called LoRa, low-rank adaptation. LoRa completely freezes the original weights of the model and just adds these tiny adapter matrices. During training, you're only updating about 1% of the total parameters. It dramatically reduces memory requirements while maintaining absolutely incredible quality. Let's compare these approaches side by side to boldly illustrate why this matters so much. Full fine-tuning of a 7B model requires over 40 gigabytes of VRAM. It's wildly expensive. LoRa drops that down to about 16 gigabytes. But the undisputed absolute default for 2026 is QLoRa, quantized LoRa. By quantizing the base model down to 4-bit precision during training, you can actually fine-tune a 7B model on just 8 gigabytes of VRAM. Guys, that is consumer GPU territory. And the output is just this tiny little adapter file, usually around 100 megabytes that you swap in and out. For sure, start with QLoRa. Only escalate to LoRa or full fine-tuning if you hit a hard quality ceiling. Which brings us to section 3. It's all about the data. Quality over quantity. I'm going to intentionally slow down right here because frankly, this is where builds either succeed or fail. It is all about the data. The raw materials you put in are the absolute most critical part of this entire process. Now, you might be wondering, and it's a question I hear constantly from builders, how many examples do I actually need to gather to make this whole thing work? Well, it basically breaks down into 3 tiers.
If you're tackling tier 1, which is just adapting style and format, like shifting tone or outputting specific schemas, 500 to 1,000 examples is plenty. Tier 2 is domain specialization, something like medical coding, and that takes about 1,000 to 5,000 examples. Then you have tier 3, capability addition, like teaching complex multi-step reasoning. That's going to require 5,000 to 50,000 examples. But listen up, because here is the single most crucial takeaway. Quality beats quantity every single time. I'm serious. 200 carefully curated, hand-picked examples will easily outperform 2,000 scraped, noisy ones. If your data has noise or errors, the model literally learns to perfectly imitate those exact errors. So please spend your time cleaning your data.
All right, section 4, the 7-stage workflow from base model to production. Okay, we've got our strategy, we have our beautifully clean data. Let's shift gears back into execution mode. Here is the highly tactical 7-stage workflow to get your model from base weights all the way to production.
Stage 1, pick an instruct-tuned base model right in the 7B to 14B range. That's the absolute sweet spot for consumer GPU. Stage 2, prepare your data into a really strict chat template format. Stage 3, configure your hyperparameters. If you're doing QLoRa, just start with a learning rate of 2e to -4 and stick to 1 to 3 epochs. Seriously, don't touch these defaults until you have a solid baseline. Okay, stage 4, run the training. And listen, here's a classic builder myth we need to bust right now. Just because your training loss graph is dropping super fast doesn't actually mean your model is getting better. It might just be mindlessly memorizing your data. Which naturally brings us to stage 5, evaluate. You absolutely must test this thing on a held-out set of data that it has never, ever seen before.
Once it finally passes evaluation, we hit stage 6, deploy. You basically have two options here. You can deploy it as an adapter only, where your inference framework dynamically loads that tiny LoRa file right on top of the base model, or you can merge the adapter into the base weights to create one single simple model file. And finally, stage 7, monitor. Look, the world changes, user inputs change, and the gap between your training data and reality is going to widen. Models drift, it's just a fact. You have to monitor your outputs daily and always be prepared to retrain. This is a continuous cycle, definitely not a one-and-done event. Section 5, how fine-tuning fails. Reality checks. Let's take a minute to talk about what actually happens when your fine-tuning pipeline inevitably breaks down. Because there are 4 common failure modes that happen to absolutely everyone, no exceptions. We've got catastrophic forgetting, we've got overfitting, where the model basically just memorizes data, then there are dataset quality problems, and finally, evaluation mismatch, which is when you optimize for the wrong thing entirely. Now, what's really interesting about this next concept is catastrophic forgetting. This is absolutely crucial to understand. It's when your model gets so incredibly good at your specific task that it literally forgets its general capabilities. You can usually spot this if you run a broad knowledge benchmark like MLU and see your model's score drop more than 5% compared to the base model. So how do you fix it? Well, always try the cheapest fixes first. Try reducing your training epochs from 3 down to 1, lower your learning rate to 1E4, or simply mix in 5 to 10% of general instruction following data just to keep its broader skills sharp. We've covered a lot, the tactical approach, the exact workflows, and how to troubleshoot the inevitable failures, but I really want to end on a thought that brings us right back to where we started. Before you boot up a GPU, before you spend days curating 1,000 perfect examples, genuinely ask yourself, do you actually need to fine-tune, or do you really just need a better prompt? If a few lines of text can solve your problem, what are you really proving by bringing in the heavy machinery?